Welcome to your first physics lab, and today's lab we're going to be talking about measurements. So the objectives for this lab are going to be to learn to use our measurement tools. We're going to be using 4 tools. We're going to use a mass balance, a caliper, meter stick, and stopwatch. If you haven't already done so, I would go ahead and watch the tutorial for the balance and the calipers. They're posted on YouTube. And then the second thing we're going to do is talk about analyzing errors. Now, as we've talked about, every measurement you make is going to have an uncertainty. So that's what we're going to be doing in this. This lab has 4 parts. Now, the order in which you do them isn't important, which isn't entirely true because you need to measure the mass and the volume before you find the density. But regardless, you can measure time while somebody else is measuring the length of the block. Now, we're going to measure length using 2 tools. One is going to be the meter stick, and the other is the caliper. And you are going to use that meter stick to a more precise version. It is a tool of science now. So to get us started, here's a video of using the meter stick. Okay, let's talk about meter sticks. I know you've used them before, but this is a physics meter stick. And if you look at the end, it has been dropped, kicked, chewed on. Who knows what the history of this thing is? But the point is, you need to not measure from the end. Well, where's a good place to measure? And it may be easy to think, well, what if I end up measuring from, say, the 10? Yeah, I'll just line it up with the 10. But whoa, hold on a second there. If you're measuring from the 10, notice that I did not line it up exactly with the 10. So if I write 10 on my lab report, I'm lying to myself, because it's actually 9.9, looks like 9.97 to me. So when you need to measure something, what do you have to do? Well, we will start measuring from some random spot. Let's just pick up this block, like so, and slam it down here. In some random place where we have no clue where it is. I'm going to adjust this so it's in a further random spot, and let's take a look at this. And now that we've got this in a random spot, we will read the left side, which I read as 16.34, note, nearest tenth of a millimeter, and then the right side. And very important, these are the numbers that go in your lab report because your lab report always has the raw data. And then when you are ready to move your meter stick to take your next measurement, you will pick up the block, as so, you will move the meter stick to a new random location, and you will set it down and take 2 more measurements. Also remember that when you read the meter stick, you need to be directly above the meter stick. So this is the only lab where you are going to record your data on the data sheet. It's the sheet attached, you'll find it in the lab, and it's got little lines with everything specified. So you'll record your raw data on this. Remember that the last column, you're going to get a plus minus, and we'll talk about that in a second. You will repeat your measurements with the calipers, again 3 measurements on each side, and then we're going to talk about the error analysis. And since you have 3 measurements, your uncertainty is going to be the max deviation from the average. Now remember that you will always report your answers as some average plus or minus some uncertainty. For part B of this experiment, we're going to calculate density. So what I want you to do, I want you to watch the video for the mass balance. That way we can talk about how to read it. Again, we always read in between the lines. Then we're going to calculate volume, and since volume is length times width times height, you'll see that these quantities are multiplied. So when we're propagating error, if you think back to that handout, we add the percent uncertainties. So you'll say, oh look, length is 3% off, width is 3% off, height is 4% off. So your error percent would be 3 plus 3 plus 4, which would equal 10%, which is a little high for this lab, but that's all right. Then you're going to calculate density, which is mass, over volume. And again, since you're dividing, you're still going to add your percent uncertainties. What I've prepared here for you are some sample measurements of length, width, and height so we can calculate volume and determine the error analysis. all these measurements are in centimeters, and they're all pretty bad. Remember we talked about you will have an extra decimal place on all these numbers because you will read your meter sticks to the nearest tenth of a millimeter. Remember that. So what I'd like you to do is to calculate the uncertainty on these three. Well, pause the video, calculate the uncertainty, and then we'll start back in a minute. So here I've calculated it out, and keep in mind you always round at the end, and here this didn't work out so nice. We only keep the first digit if it's not 1, and then we round this number, your primary number, your average, to the first digit of your uncertainty. Now here note the uncertainty is the max deviation because we only have 3 measurements. And here I have 3.5 plus or minus 0.2 and 1.5 plus or minus 0.1. But I want to find the uncertainty in my volume. So the first thing you always do is use your average quantities to get the most probable value, and rounding at the end, we see that we have 12.075 plus or minus, when you multiply or divide, what do you use? Percents. So convert these 3 into percents. Okay. So as we've done this, I've converted all these to percents in decimal places. 8%, ooh, missed a 0 there. That's 5%, and that's about 6.7%. When we add these together, we get 21.1%, which is a huge uncertainty. Yours will be better. Remember, we want to convert this as a number, so we get 12.075 plus or minus 2.548, only keeping the first digit, and then these have the same place, so we get 12 plus or minus 3 cubic centimeters. And that is how we do it. Again, less than 3 points, or less than 10 points. Less than 3 points, you should take more measurements. Less than 10 points, your uncertainty is max deviation from the average. When you multiply or divide, you have to add the percents, and then put that back in the number. All right, and you are ready to continue with the next part of your lab. For part C, we're going to be dropping a marble. And we're going to drop this marble about 10 times. But so you don't drop the ball with error. See what I did there? That's a horrible physics joke. But let's continue on. Since your n is greater than or equal to 10, our uncertainty is going to be standard deviation. So please refresh the handout. So you're going to get your time, you're going to get your uncertainty in that measurement, but how do you find the actual value? Well, your marble's going to go, it's going to fall 2 meters. You know what's accelerating it. Constant acceleration problems, just talked about this in class. So I want you to devise a formula and figure out what the actual time should be. And then you can compare it to what you got experimentally. And to show us a little more about this, here's Dr. Fox-Linton.
I'm going to be timing how long it takes this ball bearing to hit the ground to fall 2 meters. So the idea is it stops from the bottom of the ball bearing hits the ground, so I want to start when the bottom is 2 meters up. And I'm going to be starting the timer myself to cut down the reaction time so I don't have to worry about talking to anyone. So I'm just going to hit start, let go at the same time hopefully, and then when I hear it hit I can hit the stop. So here we go.
D, the final part of your lab, you're going to be using a pendulum. You're also going to be making a graph using graphical analysis, which there's also a tutorial video for. So again, watch tutorials. They will help you, and since we're going to be doing the same type of stuff, it's nice to get some it's nice to get refreshment as well, but it's nice to get refreshers on these things. So what we're working on here is a simple pendulum, and we're going to measure the period of the pendulum, how long it takes to swing one full swing. And we're going to base this off of its length. That's what we're going to graph. So what we're looking at when we're talking about length is the length from right here where this pendulum touches the metal, all the way down, well, where would it measure to? If you measure to the top, your pendulum's too short. Measure to the bottom, your pendulum's too long. So if you measure to the center, that's just right. Now the center of this ball is 2.54 centimeters, so it's 2.54 centimeters divided by 2, half an inch, but refrain from that in this class. And then what we're going to do is we're going to swing it. And we're going to use the small angle approximation, so it's 5 degrees, which is barely any swing. So you let it go. And it doesn't matter, you don't have to start right when it goes. And when it hits the edge, you'll hit start. And it's going, and you're going to count 25 times. So through the magic of time-lapse video, and 25. We will stop it, and you will record. Now, since it's a timing measurement, when is most of your error going to come from? Okay, you should be thinking about this right now as you're doing it. It should come from whenever you hit the button. So by timing it 25 swings back and forth, you'll minimize that timing error. So when you're doing this lab, again, remember, multiple swings to minimize your timing error. And then when you're going to graph it, we'll have some, well, let's talk about this for a second. If we compare this, it's going to be a linear equation. We want a straight line. So the equation for a line is y equals mx plus b, which if we start matching things up, we can see that, oh, look, period matches with y. This whole thing matches m, and this is x. Now, graphical analysis doesn't like powers to the 1/2, so what you have to do is you actually have to calculate it to the 1/2 and then plug it in. And in this case, b is just equal to 0. So when you graph this, you will get a straight line, noticing the y-axis will be your period, and the x-axis will be length over 1/2. And when you graph this, you will compare the slope from the graph with your error bounds. Again, check the tutorial for graphical analysis, with what the slope should be, and make some comments on this. Are they the same? Are they different? Why would they be different?